mistakes. So I have lots, so it's like 15 mistakes in that equation. More mistakes than degrees of freedom. That's hard to do. So I got F2 equals A2 on top. Good. So I have A2 on top, A1 on the bottom, times F1. That looks right to me. Now and I see I have A2 on top. Good. Okay, good. Is that look right there, everybody? And the beautiful thing is that if A2 is small enough, these things can be shrunk as small as I need them to be. So if I'm a really weak mechanic and I can barely push with very low force, I can keep shrinking the size of this thing. So, but what do I have to do in return? Like, there's no free lunch, right? It's supposed to be calculated how much work it takes. What's work? It's force times distance, right? So there's some downward force to gravity, mg from this car, which is what F1 is, m times g, where m is m of the car. And it's raised up some height h. That's a lot of work, right? So what is it about? So he's pumping like this. He's going up and down multiple times. I can do the same thing here. I have a pump just like it. This thing is exactly like that. There's a small thing over here and a big thing. There's also a lever on it giving me more leverage. This is an example of leverage, a mechanical advantage, right? So, oh yeah, it's all the same thing. What I'm doing is I have to go up and down many, many times to get this to go up a short distance because I'm exerting a smaller force here, right? So small force times large distance corresponds to a large force over small distance, and that's how it is I can translate from small forces, like small force from my hand is, right? And here's another example, this leverage example of this too, right? Big distance over here, small distance over here. So small force, big distance, bigger force, smaller distance, and then there's a little force acting on this very narrow tube of oil. Then it goes down as a U-shaped thing. A wider tube comes up here. Much bigger forces are exerted, but it moves very slowly. So I had to pump for a while, but now I'm gonna crack this wood in half because I can't do this. I should have picked it up by hand. Showed you I can't break this by hand, right? Despite all my efforts in the gym. So you can't see it on the big screen. Maybe well, listen for the crack if you don't see it. But I'm just gonna crack this thing just to show that it's a big force, right? Doesn't it sound awful? Ooh. Oh, that's terrible. Yeah, so I have to know my strength. I'll be able to break that piece of wood because I have leverage, right? And so we've seen 3 examples at least now in this class of leverage. This is a new one. Small area, big area, comparable pressures. Like, forget the height for a second. Suppose the car's on the ground, same height, right? So same pressure here, same pressure there. Why are the forces different? Because the areas are different. Big area here, little area here. The little area gets the small force, big area gets the big force. Same thing, that's how this was working. So we've seen leverage like this, right? Lifting the big boulder, right, by the little person, right? By having a longer distance there compared to there. That's what you might see on next week's midterm, right? These issues about static equilibrium and rotation problems where you calculate the torque. The torque from this guy's, if suppose these guys are balanced right now, and suppose he's off the ground, he's just hovering above the ground, that means that the torques must be the same. Torque from this, torque from that. The net torque is 0 if it's not accelerating, no angular acceleration. How can that be if the force from the boulder is bigger, if its mass is bigger than mine? Well, bigger arm. There's a bigger radial arm. This is the radial arm, the perpendicular distance from the pivot point to where the force acts. That's this horizontal distance right here. And this is small, that's big, big force, small force, you multiply them, it's all a wash, right? All right, equal and opposite torque. So that's an example of leverage, right? That's an example of leverage. Another one we saw was with pulleys. Remember that? If I had a bunch of pulleys, if I pull with some tension over here, it results in down here, how much leverage am I getting? If I pull with tension T here, what's the total upward force due to the ropes on something that's tied onto these lower pulleys? What's the ratio? It's bigger than 1, right? If I pull this thing over 1 meter, how high up does this thing go over here? It's just tied to the ceiling. You guys remember this? 4, yeah, 1, 2, 3, 4. Each of these ropes is shortened by a quarter of a meter, results in 1 meter over here. So once again, no free lunch. It's all the same thing. All this stuff, these are all examples of leverage where you get a bigger force and a smaller distance, smaller amount of displacement that corresponds to the opposite thing. Okay, good. One last thing I'll mention about buoyancy before going on to dynamics is the notion of center of buoyancy. So you know what center of mass is. In fact, I can show up next week, right? You know how to calculate that, how to think about it. You have conservation of momentum, no external forces. Center of mass is motion, doesn't change, its velocity doesn't change. In fact, its location doesn't change. It starts off holding still, it stays put, despite internal forces, right? But you can also have center of buoyancy. So if you have a boat and you pay the money for the boat, it's a decent boat. Here's a beautiful boat, right? If it has, like, how do you design ballast? Do you design ballast so it's really low in the boat or really high in the boat? You want to sail a boat, if you're going across the ocean, you want to have all the lead in the very bottom part of the boat or way up on top of the mast? Where do you put the lead? Bottom, yeah. This is where you want the ballast, down here. That big battleships, like those funny aircraft carriers that get really skinny at the bottom in the water, they have a lot of weight at the bottom of those ships, right? Otherwise they would tip over, which would be disastrous. You spend a lot of money on those things, so just keep on board. So this down here is where you put your mass. So what you want for a boat is to have the center of mass be really low. Now what is the center of buoyancy? The center of buoyancy is where the center of mass would have been if the submerged part of the boat were full of water. And water is equal density everywhere. It would be up here, right? So that's the center of buoyancy. Why is this good? It's good because of torque. Let's think what happens if you tip the boat over. So the boat tips over, right? So here's your center of mass, and here's your center of buoyancy. So what are the forces acting, right? Oh, I drew a little high. That's okay. The thing that matters is this is above that. You tip it over. So what happens? Well, the center of buoyancy is effectively where, if you say, well, where on the boat is the buoyant force acting? Where's the single point that's kind of effectively what's going on? Well, this is effectively where it's acting. That's where the buoyant force acts. And if the boat is floating on the surface, then the buoyant force is going to equal and opposite to the force of gravity. Where does the force of gravity act, right? Well, it's just mg, right? M of the boat times g. That's acting at the center of mass. So look what's going on. If you calculate what the torque is, let's choose. It doesn't matter. We can choose any point for our pivot point, and we're going to get the same answer for which way the torque is going. We'll get different magnitudes perhaps, but let's see. If we choose a point, let's just choose a point that's right between these two. In that case, this guy's giving you torque. It's going in the. So this is my positive direction, clockwise. Positive direction for torques. Is this center of buoyancy getting a positive or negative torque if I choose this point to be my pivot point? It's right between those two. Do people, I heard negative. People agree with negative? So most said yes, some said no. Let's check it out. The way so this is actually half of what we're doing the last few minutes in review, actually. You need to know how to calculate torque to get the signs right for next week, right? So how do you do that? The way to do it is once you choose your pivot point. So suppose it's a statics problem. You're told this boat is not moving. It's holding still. It's sitting like this. Then we can choose any point for our pivot point. I choose this point because that's how I feel. I'm allowed to do that. Any stationary point is a pivot point. So that's legal. I can still use that and calculate. Okay. So I put it in right there. See, all right, what is the torque? Sine. Well, the way to find that out is I stick a nail through that point and just have only this force acting on the object and say which way would it accelerate? Would it go that way, positive, or go that way, negative? So which is it? If I push up on this point, and I've got a nail right there, which way is it going to rotate? Positive or negative? It's got to be negative, right? This is pulling up. It's going to turn it to go that way. So that's a negative torque, but this is going to be a positive torque. Oh, am I full of malarkey? I'm wrong. They're both negative. But that's good, because what are you trying to do? You want the boat to right itself. So both of those torques are going the right way to go right the boat. That's what you want. That's why you pay for a boat that's heavy on the bottom and light on the top. And so if you imagine the other situation, if the center of buoyancy were below the center of mass, if you had lots of mass up on the mass, well, it kind of makes sense, right? It's going to fall over and stay over. It's not going to go back up like a weevil. It's going to fall over and stay down. You know what weevils are? Yeah. That's a long time ago. they wobble, but they don't fall down. And the reason for that is because they got ballast on the bottom, and it's actually not center points. I'm lying to you a little bit. They don't fall down for the reason we talked about a couple lectures ago, when you've got a round object that's sitting on a flat surface that's got ballast like that, like lead like that. In this case, it gives you a torque. So that's an example of an object that wants to stay righted. But this is related to that. But the difference is that the upward force you can think of as the buoyant force acting on the center points. Okay, good. All right, so I've covered a bunch of things. I've gone to, I think, all the stuff I wanted to cover short of dynamics for fluids. Yes? Center of buoyancy is the place where the buoyant force effectively acts, in the same way that the center of mass is the place where the force of gravity effectively acts. And if you want to think about why is that, it's because the water over here is trying to get into this space and fill it up. And if it did that, where would the force of gravity be acting on that water? It would be right at the center of mass of the water in this volume. And that's what that is. That's where the center of mass of the water would have been, had this been water inside this submerged volume of the boat. So if the mass of the boat is concentrated below that, you get a stable situation, it wants to do this. If it's the other way around, then you hope you brought your swimsuit. Yep. The center of the volume. It's the center of mass of the volume that's submerged, assuming equal density throughout that volume. Although for this time, I might as well think of it as area, right? Because we'll assume the boat is the same shape and it has flat ends or something. So yeah, it's just the area. That's right. Yeah. Anyway, all right. Good questions. All right, so now let's think about dynamics a little bit. Let's look at this demo. So here I've got a tank of water, and it's got corks in the sides, got holes at various heights. And what I'm going to do is I'm going to pull the corks out and get really wet. That's why I'm not wearing my tuxedo today. And when I pull this out, these things are going to, spouts of water are going to come out, right? Just like you see when you're at home and you're in bad mood, you take your pencil and put it inside your milk container, whatever you do. It's none of my business. It comes shooting out. Which one is going to come out faster? Some of you already responded to that. So which one's going to come out faster? The one's at the bottom or the top? Top? Bottom? The bottoms have it? I think you're right. So let's check. I'm going to turn on the water first. See if I do that. There's no overflow, so if I get it wrong, then I'm going to get wet. Oh, all right. There it goes. Sure enough, the bottom comes out faster. Does everyone see that? We know it because look, it's following a parabolic trajectory because water is just like everything else. It's got to follow the laws of physics. Laws of physics say that a parabolic trajectory for projectile motion. So here it comes, right? And it's shooting out faster, and you can tell that because it's making it further out before it hits the ground. Whereas over here, it's sort of dribbling out. This guy too, right? It's even less, right? You get the picture. All right. There's even another one. Oh, now it's really getting it. Okay. All right. All right. Why? How come? Ooh. And you guys knew the answer. Most of you. Some of you weren't sure, and some of you got the wrong answer. But that's great, though. The best thing, I'm thrilled when people actually get wrong answers to these questions. I know some of you are just humoring me, I know. But it's good because, don't tell my mom I'm drying my hands off my pants. All right. I was off camera, hopefully, though. So the bottom line there is just that the bottom one is faster. And why is that? It's because the pressure down here, is the pressure down here bigger or smaller than the pressure up here? It's bigger down here. And that's right. And pressure really is a type of potential energy. It's like a force from a spring. So that's why it is. So the first thing I did in class, I just wrote it down, so we're going to need it over and over. I wrote down Bernoulli's equation. Pressure 1 plus rho 1 g times h1 plus 1/2 rho 1 v1 squared equals that same formula with 2's under it. What does that mean? It means that energy is conserved as you follow a continuous flow of water through some system. So if you think of the water at the top of the tank flowing down and coming out of one of those spouts, that's a continuous flow of water. And it has to follow, it must be the case that any 2 points, 1 and 2, anywhere along that flow, must obey that equation because energy is conserved. This is actually, each of those terms is an energy per unit volume. So pressure is not just, doesn't have units of energy, it's units of energy per volume, right? A force per area is an energy per volume, right? Yeah, that's right. So, and that's good. The 1/2 rho v squared, same thing, right? That's the term we haven't used yet, but now we have to think about it because the water was moving. So when the water starts moving, there's other kinds of energy you can have besides potential energy due to gravity, the rho gh term, and besides the pressure in the water, which is like a potential energy like a spring, you know? So how do we calculate it exactly? Well, here's what we do. You draw a picture of the situation as always. You say, well, okay, I know the surface of the water is right here. The pressure just above the surface, let's do this in absolute pressure. So what's the pressure just above the surface? 1 atmosphere. 10 to the 5 pascals, right? What about just under the surface? What is it just under the surface? Again, it's 1 atmosphere, it's just under. Now, if we go down some distance h, now pressure right here, right? Let's call this point 2 and this point 1. So P1 equals 1 atmosphere, P2 equals what? Well, 1 atmosphere plus or minus. Bigger or smaller down here? It's bigger, plus rho gh, correct? Now we've got a hole in the side, and water is streaming out. So now we've got to figure out what's going on at point 3, okay? What's P3, first of all? Well, here's the way to think about that. When the water's inside the tank, it's under pressure because there's a bunch of water on top of it. When it goes out that hole, now it's free, right? It comes out, and it's not under pressure anymore. It's flying through the air, but it's not crushed under all that water anymore. So what do you guess the pressure to be of a drop of water right here that's flying through the air? So I heard zeros and ones. Those are both correct answers, but I want absolute pressure. What's the answer in absolute pressure? 1 atmosphere. So P3 equals 1 atmosphere. Great. That means that we know the pressure here. And what are we asked to find? We're asked to find velocity 3. We want to know how fast is the water traveling right here. That's the question we're asked to solve. We know how. We know H. You know, what are we given? We're given H. We're given density of the water. We're given what else? I think that's all we need. That's all we need. So to figure this out, use Bernoulli's equation and label it to the grader. Sleep deprived graders got 300 exams, 350 exams to grade. So we have Bernoulli's equation. What does it say? It says pressure 1 plus rho g h1 plus 1/2 rho v1 squared. I didn't bother to put 1s on the rows because it's all water. Water's got constant density. It's incompressible. You can't compress water. It's always the same density everywhere. Same mass per volume. What does that equal? Equals P. Oh, sorry, 1, 2. Yeah, 1, 3. So let's compare with Bernoulli's equation, just like with conservation of energy of any form. You can compare any 2 points you want. You don't have to just do 1 and 2. You can do 1, 3. You could have done it 1 to 2 and then do 2 to 3. But let's get to the chase. We'll go from 1 to 3. Okay. So we got P3 plus rho g h3 plus 1/2 rho v3 squared. And so right away we say, okay, that's 1 atmosphere right here for this, right? Rho g h1. What is h1? Well, let's just make our life easy. Call this the y-axis. We'll say this is height h. This is height 0. I can do that. That means this is rho g h right here. H with no subscript means that difference in heights, right? Plus 1/2. Oh, what is the velocity of the water up here? Well, you might say, well, it is actually falling. The water is falling up here a little bit. But if this area is really big, it's not falling very fast compared to the water, so I can neglect it. But it depends on the question you're asked. In some questions, you have to relate them. And the way you do that is using the continuity equation, which I have not introduced yet. I'm introducing it in about a minute. But for right now, we'll just take the approximation. This is really big, and this hole is really small. In that case, the water up here is not moving very much. It's falling so gradually we can ignore it. After all, kinetic energy goes like v squared, so small things get really small when you square them, right? So we ignore it. So good. 1/2 but that's going to be 0, right? And what does that equal? It equals pressure at point 3. Right. Oh, and what did we decide pressure at point 3 was? What's the pressure of the water right here? It's 1 atmosphere. It's the same. So that's just going to cancel out, right, on both sides. And so what are we going to add to that? Rho GH. Oh, yeah, but H3, we defined our y-axis, so the height of point 3 is going to be 0. That's 0. And then what are we going to get here? We're going to get 1/2 non-zero v, so 1/2 v3 squared. And this is the thing we're looking for. Good. So we now got an equation, one unknown. I'm sitting pretty, right? When I isolate it squared, I take a square root. But this is how I solve for it. So this is the way you use Bernoulli's equation to figure out how fast the spout is coming out, water's moving out of this thing, right? We could have also had a problem where there's some tube like this, and it goes like that. Water's coming in over here. There's V1 over here. There's some area 1 of the tube. There's pressure 1 of the water right here, et cetera, et cetera. And then over here it's 0.2. So this is a different problem I'm describing now. I'm saying, well, oh yeah, just to follow up. So just calculate the velocity. You just isolate for V and you'll be done. But you see, this is how, because of h here, the bigger that distance h is, the faster V is going to be. This gets bigger when h gets bigger. And that's why when you get lower and lower, the speed of the water coming out is getting bigger and bigger, right? Yeah? All right. Lickety split. I know we're moving so fast in this class. It's a true fact. So V1 comes over here, V1 comes out over here. Will it come out faster or slower if this is the smaller end of the hose over here? Faster. Yeah. Has to, because of the continuity equation. You can't lose mass somewhere in the middle. There's no little wormhole that sends it off to another universe. You got to have whatever water comes in over here is going to come out over here, right? So this is A2. This is pressure 2. Is the pressure bigger or smaller over here? I would have guessed bigger, but it's smaller. So we'll think that through. So what do we need to do to figure that out? The way to figure that out is with one more equation. So we've got an equation. We have Bernoulli's equation, which we use over and over again in fluid problems. We also have the continuity equation. Continuity equation. Spelling will not be on the exam, thank God. All right, continuity equation. So the continuity equation says that if you have some mass of fluid entering in over here, it has to come out over here. So suppose you've got some fluid that's coming in for some length of time. Well, here's how far the fluid would move. So there's some volume of fluid in this little cylinder here, right? Well, the same volume's got to come out over here. But look, it's going to be much bigger over here, right? Because to make the same volume of fluid as you have here over here, well, it's a smaller area, you need a longer length. Does that make sense? And if this length represents how far the fluid gets, a little piece of fluid gets, molecule just going along, in the same length of time, delta t, it's got to be going faster. And you all have intuition for that. You said, yeah, faster here. Yeah, but this is sort of a formal way to think about that. And so what is the continuity equation? It says V1 times rho 1 times A1 has to equal V2 rho 2 times A2. It says that if you have a bigger area here, and you say, wait a minute, you have different rows here. That's true. This is a general equation for any type of fluid. Let's write it down for incompressible fluid. So for incompressible fluid, for example, water, right, a liquid like water, right, then you have a simple equation. Rho 1 equals rho 2, you can cancel them out. So it's a simple equation. V1A1 equals V2A2. Sounds like a robot from an old movie, right? Okay, so there you have it. So that continuity equation tells us that if you have twice as much area, you're going half as fast. Which makes sense, right? Now, it's the opposite of the way traffic works in the freeway. When you go to 5 lanes to 2, it slows down. So students always get confused by this. They start going from 5 lanes to 2 and it speeds up. Well, if cars were packed bumper to bumper, moving at freeway speed, and they continue to do this and they were incompressible, right, it would actually be the case that when you went from 5 lanes to 2, you'd have to speed up. It's the only way you get the cars through, right? It's just that what happens with real drivers and real cars is there's distance in the cars and you get shorter distance when you start to come in. And then, anyway, it's a complicated process. But people's intuition is not based on incompressible fluids. Your intuition is based on driving the freeway. You get confused. So continuity equation. Now we've got all the equations we need. If we're going to actually take these things and apply it to the problem of figuring out what the pressure difference is, well, here's a demo for that. So in this demo, what I'm going to do is I'm going to run fluid through a pipe at the bottom of this device. I'm going to tell you a very important fact about how to use it. You think they're a little counterintuitive about how you do calculations with them. Oh, good, you can see it. So there's a pipe at the bottom. I've got water pouring in up here. It pours down, goes through this pipe. And these things are called stand pipes. They're standing up, and they have water that's standing still inside each pipe. Here's the conceptual thing that's important that you should know for trying to solve the problems that we can have for the final. The water that's in these standpipes is being used to measure the pressure underneath each standpipe. But when you think about using Bernoulli's equation, between point 1 and point 2, you can't use Bernoulli's equation to relate what's going on in this flow of the water down here and some point up in the standpipe, because it's not a continuous flow of water. The water that's coming in over here is flowing in, it's going along down here and out the other side. It's not coming out these standpipes, otherwise it would be flowing out of the standpipes, but it's not. So that means you need to have a different rule for relating the pressure inside of the water into the standpipe to the pressure inside the tube down here. And that's a little counterintuitive. Another way to think about it is suppose I put cellophane underneath each of these standpipes so the water can flow in and out. It wouldn't change what's happening. When I let water start flowing, I'm going to do it right now. I turn the water on so it's flowing through these pipes. If I can figure out which of these nodes is the right one. There we go. Whoop, it's a little too fast. Oh, of course I have to take the cork out. Ooh, there we go. Ooh, that was a little too much. All right, so now I'm going to turn it back up again. Stop getting this just right with dynamics. All right, that's really moving. Wow. So there's a couple things to learn from this demo. The first is how to think about standpipes. So I'm going to emphasize that again. Water is flowing down through this tube and along this bottom tube at the bottom of the device. There are standpipes on top of it, and there's water standing. But look, the heights of the water are different in different places. You see that? Can you guys see it? It's kind of hard to see. I'm going to turn it down a little bit. I'm going to do this. I'm going to slow the water down a little bit. So what you notice, first of all, the first thing to notice is that water's not shooting out of the standpipes. The next thing to notice is that the water over here has got pretty high in these standpipes, but it's lower in these. It starts to come back up again for this one. Here, I'll